Hello and welcome back to my Physics Online video lecture series. In today's video, I wanted to look at vectors, and so this is basically the third lecture of my series, and it's going to be basically just part one of this lecture, in which I want to look at basically the mathematical properties of vectors in general. And so before I dive into that, I wanted to look at what our motivation is for using vectors in 2 dimensions and 3 dimensions and so on. And we have basically looked at motion so far in 1D. And by motion, I just mean the kinematics description of motion. So we have only been able to describe the motion of objects that are constrained to move along a particular path. So for example, a train which is moving on tracks is basically constrained to stay on those tracks. It's going to be moving either straight forward or straight backward. So you can make a 180-degree change of direction by going in reverse, but you're not allowed to turn by making, say, a 90-degree change of direction over a smooth curve. These 1D motions are also okay if we're looking at sudden sharp changes of direction. A sudden sharp change of direction might be considered, for example, maybe you're looking at a beam of light, and the beam of light is coming out of a laser, so it's moving along some straight line. It's a nice collimated beam. And then there's a mirror, so it hits the mirror and bounces off. So there's a sudden sharp change in direction at the interface where it hits that mirror. So actually 1D motion does okay with describing that, so long as you recognize that there is this sharp change of direction at that point. And in fact, a lot of simple ray trace software that optics engineers, for example, might be using often will make the approximation that everything is in a one-dimensional motion. Or if they want to look at stuff that's focusing, maybe there's 2 dimensions in it. This, however, this 1D approximation, while it describes some motions pretty well, it is not going to describe a large number of motions that actually exist in nature. For example, if you're driving a car, you don't usually make sudden turns. Rather, you tend to go around a corner. Even if you're turning at an intersection, it's not a sudden sharp turn per se. It's usually you kind of round the intersection, if you will. And so if you wanted to describe that entire turning motion, you need more than one dimension. Ditto for if you want to look at a planet that's orbiting its star, or a moon orbiting its planet, or what have you. Anything orbiting tends to be in actually an elliptical orbit or hyperbolic orbit. On rare occasions you might get an actual circular orbit. So all of those things require 2 dimensions. You can drop a ball in 1 dimension, or you can throw it straight up into the air, or throw it straight down, but you can't throw it in any other direction, forward, or like a pitch you might throw up and forward, or if you're playing outfield and you're trying to throw in to the base, you kind of throw up and forward to get it there. A long distance throw, in other words. You can't do anything with like shooting a rifle at a target or any of that. So this is our motivation for wanting to go into vectors that are more than one-dimensional. And a lot of these motions that I actually just described are 2-dimensional motions, or can be described as 2-dimensional motions with very good accuracy. Sometimes we even may need to go into 3 dimensions. For example, maybe you have an airplane which is trying to land, and it has not a headwind, not a tailwind, but sort of a wind that's buffeting it from the side. So the wind is coming from one direction, the plane is traveling forward in one direction, and it's traveling down in a third direction. In any case, if we want to go into 2D or 3D motion, we basically tend to want to choose our dimensions that they're perpendicular to each other, and very often once that choice has been made, what happens along one dimension has little effect along with what happens in the other direction. So what this diagram is actually showing here is a sort of motion diagram for a ball that has been dropped straight down. That's the red ball. And one that was initially thrown straight forward but is also falling. So maybe it's on top of a building, and with your left hand you drop the red ball, and with your right hand you throw the blue ball straight forward. And so initially the red ball is falling, and then it gets a little faster, it gets a little faster, it gets a little faster, it gets a little faster. Still falling straight down. We're assuming no air resistance here. The blue ball, on the other hand, has been thrown straight forward, so initially there's no downward component to its motion, but as time goes, the gravitational acceleration pulls down on the blue ball, and so it actually starts falling as well as moving forward. And you'll notice that the black arrow, which represents basically the horizontal velocity, is not changing in frame to frame to frame. And you also may notice that the green arrow, which is representing the vertical velocity, is the same for the blue ball as for the red ball in each of these frames. So this black forward motion is not having any effect on the downward green motion, and vice versa. We will not just be looking at vectors, by the way, in kinematics. We'll encounter them in further topics as the course goes on. In fact, the next topic after kinematics will be forces, and one of the first things that we look at in forces is Newton's first law, which involves adding forces together where forces are vectors. So, and often these vectors will be in 2 or 3 dimensions. And then again, as we get even farther into the course, we'll look at statics, which involves both balancing forces and balancing torques on an object, and so we end up with 3-dimensional motion, 3-dimensional vectors there as well. So let's talk about some of these properties of vectors as opposed to scalars. So far we've actually looked at a few properties of vectors as distinct from scalars, and we've done that in the context of kinematics in one dimension. And so, for example, we've looked at scalars such as the distance that an object travels, or the average speed, or the instantaneous change in speed. Any of those things that all you need to know is a single number with its units. The thing has a speed of 15 miles per hour, or 6 meters per second, or its speed has changed by 2 meters per second that the motion has gone on. In other words, 2 meters per second squared. Or the thing has traveled for a total of 20,000 leagues. All of these things are scalars. On the other hand, we've also had vectors, which have given magnitudes but also directions. So the magnitude and direction combine for position. Maybe I'm standing in the corner of the room and I say, well, the thing is 30 meters to my left, or the thing started at 30 meters to my left and is now 20 meters to my left, so it has had a displacement of 10 meters to the right, or to my right, I should say. The thing is moving over those 10 meters in 2 seconds, so it has a velocity of, on average, 5 meters per second to the right. So to give a quick analogy, by the way, to illustrate the difference between these scalars and these vectors, let's consider distance traveled as opposed to displacement. Consider a car. So most cars have an odometer somewhere inside of them, and that odometer sits on the dashboard and tells you how far has this car been driven. And if you put the car in reverse, the odometer still counts up, and if you go forward, the odometer still counts up. So if you decide to drive cross country and you put 6,000 miles on the car, you can expect the odometer to go up by 6,000 miles. And if you decide to then reverse that trip, literally drive the car in reverse for the 6,000 miles cross country, well, you might get pulled over a few times and you might get some funny looks at the drive-thrus, but your car will still add another 6,000 miles to it. So after doing these two trips, 12,000 miles will have been added to your odometer. Now imagine that you take the car and instead of driving cross country, you just put it on a long straight road, and you have your odometer. Maybe the odometer is very, very fine, and so it counts up in meters instead of miles or tenths of a mile. And you attach to the back of your car the end of a tape measure, and the other end you give to an observer who stands still in place. Now this is a nice imaginary tape measure. It can unfurl as long as you need it to, and of course, as you know, when you pull a tape measure out, if you walk away from the tape measure, the little measuring tape gets longer, but if you turn around and walk back towards it, the measuring tape gets shorter again. So imagine that the measuring tape is attached to the back of this car and you drive the car forward by 15 meters. So your tape measure now measures 15 meters and your odometer now measures plus 15 meters. Maybe it's a brand new car, so your odometer measures 15 meters. Then you shift it into reverse and drive backwards another 5 meters. What's that going to do? Well, the odometer has to add 5 more meters. The total distance you've traveled is 15 plus 5, 20 meters. The tape measure, on the other hand, is going to retract a little bit so that instead of saying 15 plus 5, it'll say 15 minus 5, 10 meters. So your tape measure is actually giving you a measurement of the displacement, or at least the magnitude of the displacement. You have to then specify direction. Whereas the odometer is telling you the total distance traveled. So with that said, one last little thing that we did differently for vectors and for scalars is that vectors were denoted using a little arrow over the top. So this A right here is a vector. And the other thing that we sometimes did was if it was in the main body text as opposed to an equation, we used bold font to denote a vector. And scalars, on the other hand, are denoted without the little arrow on top. This means that a vector can actually be expressed as a combination of separate coordinated scalars. So this is a vector in 3 dimensions. The vector is A, and it's specified by 3 scalars. One that specifies the x, one that specifies the y, one that specifies the z. These scalars, by the way, can be positive or negative, and that gives the direction aspect of this vector. So, for example, A might be 1, 2, 3, and it always goes in the order x, y, z. So the x direction is first, the y direction is next, the z direction is third. So 1, 2, 3 might mean if we've decided that x is forward and y maybe is to the left, then z is straight up, or maybe x is to the right and y is forward and z is straight up. Then using that latter one, 1, 2, 3 might mean you took 1 step to your right, you took 2 steps forward, and then you climbed 3 steps up a ladder. So those are all properties that apply mostly to one-dimensional vectors, although obviously I used one 3-dimensional example in there to illustrate vector versus scalar. Now we're wanting to move from one dimension to two dimensions. So in one dimension, when we were looking at motions, for example, everything was collinear, or in other words, parallel, in the exact same direction or in the exact opposite direction. So the thing would have a velocity which is in the exact same direction or the exact opposite direction as its acceleration. And therefore, all of our direction could either be a positive or a negative number. Notice, by the way, that this implies that that three-dimensional vector could almost be expressed as a set of one-dimensional vectors, and in a sense that is what it was doing. Examples of 1D motions I've already kind of talked about. Throw a ball straight up in the air, then initially the velocity is up, the acceleration is down, the displacement starts increasing, the velocity decreases, the acceleration stays constant, you reach the top, now the velocity is zero, the acceleration is still down, then the direction of the velocity is down, and so on. What we want to do is consider stuff that's in more than one dimension, and so this is going to be stuff like a ball being thrown forward, where initially the velocity is in the x direction, but the acceleration is in the y direction. Another example is a boat might try to drive straight across a river that has a current in it. The current usually is going downstream. The boat maybe is aimed straight across the river, so these two directions are opposite. This is two different velocities that are opposite, and we'll look at that in part 3 of this vector lecture. So what we need here is a few properties of vectors. So the first property is the equality of vectors, and the equality of vectors basically says that two vectors are equal if they have the same magnitude and the same direction. What that means is that a vector can be moved parallel to itself, and the vector is unaffected by doing this. So this vector, this vector, this vector, and this vector are all equivalent. Mathematically, that's true. Should make one note here about the physics of the thing, which is that usually we have some particular position that's an initial position, or some particular velocity that's the initial velocity, etc. So that generally determines where the exact start of the vector is, and therefore where the exact end of the vector is. But the point that these are all equal comes because you can see that the length is the same and they're all parallel to each other. And what that allows us to do is, if we wanted to add two vectors together, we can do it via tip-to-tail addition, which we'll look at in part 2 of this lecture. So if I wanted to add this vector and this vector together, I could move them so that this vector starts off here and ends off up here somewhere, and now I've found the sum of these two vectors. Okay, next property is what is the negative of a vector. So the negative of a vector has to have the same magnitude in the exact opposite direction as the original vector. So in these Cartesian coordinates, what that means is if a is ax, ay, az, the negative a has to be negative ax, negative ay, and negative az. And similarly, if a vector is added to its negative, the resultant vector is 0. So a plus negative a equals 0, which is the same thing as saying a minus a equals 0. And that's the same as 0, 0, 0. So subtracting one vector from another is equivalent to adding the negative of that first vector to the second vector. So I want to look at maybe a very short example of that, something really simple. Let's say that you have vector A, and that vector A is given by, for example, 1, 3, 5. then that means that negative a is given by negative 1 comma negative 3 comma negative 5. Okay, this also means, for example, that negative a is not the same thing as, say, 1 comma negative 3 comma 5. This is not equivalent to this. This right here is negative a, this is positive a. So if you were to add this one to this one, you'd get 1 minus 1 is 0, 3 minus 3 is 0, 5 minus 5 is 0. On the other hand, if you were to add this thing right here to this one, you'd have 1 plus 1 is 2, 3 minus 3 is 0, 5 plus 5 is 10. So you don't get 0, 0, 0. Okay, second property that I wanted to look at is what happens when you multiply, or for that matter divide, a vector by a scalar. Now it turns out, by the way, that you can multiply two vectors together. You can also multiply a vector and a scalar together. You can also divide a vector by a scalar. And these are the basic operations that we'll ultimately need in class. For today, I just want to look at right now what happens when we multiply a scalar times a vector. And it's actually pretty straightforward. If you have a scalar, in this case 3, and you multiply the vector a by that scalar, then you get 3 times the ax, comma 3 times ay, comma 3 times az, where a was originally ax, ay, and az. So notice two things here. One is that the total magnitude of this new vector will be multiplied or divided by that scalar. So this new vector is 3 times as long as the old vector. That's the first. The second is that the direction itself remains unchanged. So this is like adding a plus a plus a together. 3 parallel vectors, the final vector ends up being parallel to all the originals. Worth noting that there's a piece of terminology that we will look at a little more in part 3 called a unit vector. So that means that the total magnitude of the vector is 1. And we'll look at how to find the magnitude of the vector later. So let's look at another example of this just to put some numbers to it. Let's say that you have a vector such as, our old a vector was a is equal to 1 comma 3 comma 5. So you have that as your a vector. Then 3 times that vector a is going to be equal to 3 times 1 is 3, 3 times 3 is 9, 3 times 5 is 15. Okay, and similarly, if you wanted to have 2 times a, you'd get 2 times 1, so that's 2, comma 2 times 3, comma 2 times 5. Okay, so that is multiplication. For that matter, you can also do division. Maybe you want to know what is 1/2 of a, and so that would be 1/2, comma 3/2, comma 5/2. And you could keep track of significant figures for the physics if you so desire. Okay, so I've kind of hinted a little bit about how addition and subtraction are going to work. Here are some general principles, and we'll look a little more in depth at this in part 2 of this lecture. The basic principles are as follows. Scalars can be added or subtracted from other scalars. Vectors can be added or subtracted from other vectors. But a simple scalar cannot be added to a vector or subtracted from it. Similarly, dimensional analysis still applies. So the units of two vectors that you're adding together have to agree, and what that also means is that the units of each component must agree. Typically, in this kind of a physics class, our vectors are going to have the same unit for each component. So a displacement will have units of meters, and each component has units of meters. However, there are sort of specialized vectors or matrices that act as vectors in which you could hypothetically, give different units to each component. I'm not really going to go into that today. So this brings me to the last point about addition, and for that matter subtraction, which is called the commutative law of addition. And what this means is basically that the order in which you add vectors does not matter. That's the same is true for subtraction, by the way, because subtraction is the same thing as adding a negative. So A plus B, vector A plus vector B, is the same as vector B plus vector A. And graphically, I show that down here. So this is an example of tip-to-tail addition. So basically the colored vectors are the four vectors that are being added together. The black vector is the resultant, and you'll notice that in each of these cases the black vector is the exact same. In other words, it's parallel to the black vectors here, 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 same length and everything. And that's because the orange vector is the same in each case, the blue vector is the same in each case, the purple one's the same in each case, the red one's the same in each case. And so it doesn't matter what order I go in, as long as I add these same four vectors together, I will get the same resultant vector at the end. So if I start with orange and then go blue, purple, red, I get the same thing as if I go red, orange, blue, purple. And I get the same thing if I go purple, orange, blue, red, and the same thing if I go blue, red, purple, orange. Order does not ultimately matter. In this particular lecture, I didn't really draw a whole lot of figures from elsewhere, so maybe this slide is a little more boring than usual, but here are the sources that I pulled some of my diagrams from. Most of them I made myself. So I guess thanks to OpenStax, and thanks to Cengage, Survey, and Vuel, and thanks to all of you for watching. I hope that you found this helpful.